Hi. In today's video, we're going to be talking about the differences between nucleophiles and bases, and sometimes this difference is quite subtle. So let's go ahead and start. So the first, we're going to consider the steric options between nucleophiles and bases, and how sterics has a role in if something's going to be a nucleophile or a base. So if we look at a series of oxygen-containing bases, so these all have the same element that the negative charge is localized on. You have hydroxide, methoxide, isopropoxide, and T-butoxide. And so let's look at if they're going to be a nucleophile or a base as we go down this series. So hydroxide is small and it's quite basic, and so it's going to be both a good nucleophile and a good base. Methoxide is also relatively small, and so it's again going to be a good nucleophile and a good base. Now, once we go to isopropoxide, this molecule starts to get significantly larger than methoxide. And that's again because these flanking methyl groups have these hydrogen atoms that are occupying three-dimensional space. So now you have a little bit more congestion when you're trying to act as a nucleophile. And so as a base, it's still really a strong base. As a nucleophile now, it's becoming a weaker nucleophile. And now when we go to T-butoxide, now we have an extreme scenario where there's a lot of steric congestion around the basic oxygen atom. And so that is going to still allow it to act as a base, but it's going to really disturb its activity as a nucleophile. So we actually call this a non-nucleophilic base. This is a class of organic compounds that are really useful when you're trying to do elimination reactions, for example, if you're trying to promote elimination over substitution. Another example of a non-nucleophilic base is this molecule called DBU, and the full name is actually quite long. I'll just leave it as DBU here. So let's look at the role of electronics, and this pretty much follows our exact trend from when we're looking at acids and bases. So you look at stability in terms of what is going to be the most basic. And so the most basic of this series is going to be the deprotonated methane, and it's also going to be the most nucleophilic. Now if we go to the neutral forms, we have methane versus ammonia versus water. You see that actually ammonia now is going to be the most basic and the most nucleophilic, and that's simply because the methane doesn't have a lone pair of electrons to participate in these types of reactions. Let's look at the role of size and polarizability, and we're going to focus now on the halides, but this trend applies to the chalcogens and other atoms as well. So for example, oxygen versus sulfur versus selenium going down the periodic table from oxygen, or nitrogen versus phosphorus versus arsenic going down that row of the periodic table. But we're just going to focus on these halogens for now. So if we remember from our acid and base understanding of these, the iodide is the least basic. Another way of saying that is it's the most stable of these three. But once you put these into polar protic solvents, now you have to worry about the solvation sphere, about how these are going to act as nucleophiles or bases. And so in the case of an iodide, it is actually not very well solvated by the solvation molecules around it. It's actually highly polarizable as well. Ends up being that iodide is the most nucleophilic of this series. So this is against the normal trend. This is also true of sulfur versus oxygen. So sulfur is more nucleophilic in aqueous environments, and that's often when we talk about biological settings where sulfur is found. Fluoride, on the other hand, is tightly solvated by the solvent around it, and as a result, it ends up not being very nucleophilic because it can't break free from its solvent cage. Now, when we move these same anions into a polar aprotic solvent, for example, in DMSO, the trend is actually reversed. So the trend now follows this understanding of being most basic and most nucleophilic, and least basic and least nucleophilic, again in the context of DMSO. Now let's look at a few examples of molecules that we will always be treating as nucleophiles in our organic reactions, and that is an acetate, often shown as sodium acetate, an azide, often sodium azide, and cyanide, often sodium cyanide. It can also be potassium salts of these various ions, one of the things I want to draw your attention to is that all of these structures have resonance structures, and all of them are weakly basic. That is, the pKa of the conjugate acid is about 5. So they're not strong acids, and they're not weak acids, but they're weakly basic. So they're not going to act as a fantastic base. They will more likely act as a nucleophile. All right, well, thank you for your time, and I look forward to seeing you next video.